Okay, these notes are about understanding limits graphically and numerically. First, what we're going to do is we're just going to recall the proper notation on how to write a right-handed, left-handed, and general limit. So for a right-handed limit, we write this as the limit as x approaches c from the right side of f of x. In words, that is the limit as x approaches c from the right. Left-handed is limit as x approaches c from the left of f of x. Same thing verbally, but instead, obviously, from the left. And then lastly, the general limit takes into account both sides. So this is as the limit as x approaches c of f of x. Okay, so the limit as x approaches c. Okay. Example 1 says, look at the equation f of x, and it wants us to analyze it based off of the graph and just see if we can remember some simple tasks from Algebra 2 and apply that knowledge to limits. So first, it wants us to factor and simplify. So for the numerator, to factor 3x squared minus 8x minus 3, that is 3x plus 1 times x minus 3. And then the bottom is a difference of squares, so this is just x plus 3, x minus 3. And if you need any help with factoring, I highly suggest you go back and look at some of my Algebra 2, Algebra 1 notes. Okay, now I'm just going to see if I can simplify anything, and that would be the x minus 3 that I can cancel out. So I am left with 3x plus 1 over x plus 3. Okay, now it says to find the coordinates of the whole. So what this is a point of discontinuity. We know that point of discontinuity is wherever we canceled out. So that's that x minus 3. We're going to set that equal to 0, and we get x is equal to positive 3. We're then going to plug that 3 into our reduced function to find our y value. So this is 3 times 3 plus 1 divided by 3 plus 3, which gives us 10/6, which is 5/3. So that means this whole right here is 3, 5/3. And then our domain, when looking at this, we have to keep in mind not only the whole that we just identified, but the vertical asymptote. So when writing this, this would be negative infinity to negative 3, union negative 3 to 3, union 3 to infinity. And that is keeping in mind the vertical asymptote and the whole. Now looking at the range, we're going to be looking at the y value. So we need to keep in mind the horizontal asymptote and then also the y value of the discontinuity. So this becomes negative infinity to 5/3, union 5/3 to 3, union 3 to infinity. And again, because of the whole and the horizontal asymptote. And then lastly, for this one, it's do you remember what variable goes with what? So the vertical asymptote is going to be x equals negative 3, and the horizontal is y equals positive 3. Okay. The next example is having us understand the proper notation, so the pre-calculus notation versus the calculus notation. However, when talking to all of you about who you had last year, I am confident that you not only know the pre-calculus notation, so the one that you see on your notes, but also the calculus notation where we that we wrote in the beginning of the notes, where we had the limit as x approaches from the right or from the left of the function. So what we're going to do here is we're going to look at this graph and answer the following. So here it says, as x approaches negative infinity, f of x approaches, well, negative infinity, okay, is going this way, negative infinity. So as x is getting more and more negative, okay, what is happening to the function? Well, as this is getting more and more negative, we notice that our function is getting very close to our asymptote here at 3. So we would just say that the answer is 3. The next one, as x approaches infinity, okay, as x approaches infinity, so as it's going in the positive direction, we see that, again, our function is slowly approaching that asymptote of 3. Okay. Next is as x approaches negative 3 from the right. So negative 3 is right here. And then we're going to assume this is in a little interval here, a boundary on each side, and we're only going to look from the right. So looking from the right side here, that would be this function. Notice that as it's getting closer to this negative 3 here, it's going down towards negative infinity. So I would write negative infinity. And then right below it, it's the same one, as x is approaching negative 3, but now from the left. So now we're looking at the other side, and that is the left side of this. And notice we only see this function here, and as this is getting closer to negative 3, it is going towards positive infinity. And then next, we have the example as x is approaching positive 3. So I'm going to change my colors up here, and now we're looking at positive 3 right here. And the first one is approaching from the left. So this is the left side of the function within that interval. Well, as we are getting closer and closer to that value of 3, our graph is getting closer to the y value of that whole, which is 5/3. And then you'll notice, even when we're looking on the opposite side, the right side, as we are approaching 3, it's still approaching that y value of the whole, which is 5/3. So in other words, the limit is the y value that the graph is approaching from both sides. So the limit is the y value that the graph is approaching from either side. Okay. Now let's dive into this a little bit more using that calculus notation of limits. And let's go ahead and look at example 3. Okay. So the first two parts right here where it has A and B. Hey, I don't want this to throw you off. Okay. This is just seeing if you remember function notation back from Algebra 1, Algebra 2. That's it. Okay, so when looking at these, remember whatever's in those parentheses is the x value. So f of 2 means we go to the 2 on the x's and we see which one of the y values correspond to that. Well, we can go up and meet a function, and we can also go down and meet a function, but the only one that matters is this one right here at y equals -1 because it's a closed dot. So this is equals -1. And then part B, f of -1. So here's -1. We are looking to see where this function meets up on the y-axis, so we can only go up. Well, it can't be 2 because it's an open circle, so we have to continue going up to that closed dot where the answer has to be 4. Now, for the limits, when we are answering them, the open and closed dots don't matter, okay? They don't matter for the simple fact that as we are getting closer to that value, we're just seeing where we are getting closer to a y value. Even if that y value at a certain point doesn't exist, that doesn't mean that the limit doesn't exist. So now let's look at C, where it says as x approaches 4 from the left side. Okay, so I'm going to do my limits around 4. Okay, so here's my 4. So I'm going to draw my limits around 4. Okay, and then I'm looking from the left side, so that's this left side right here. Notice as this little portion is getting closer to my x value of 4, it looks like it is stopping at the y value of 3. So my limit as x approaches 4 from the left is 3. Let me see if they have one for the right. So that's -4. No. Okay, so now let's look at D. So D is looking at 2 from the right, so I'm going to erase this so I can redo it. Okay, so here's 2. Okay, so here's my interval around 2, and I'm only looking at the right side. Okay, so the right side is just this function within that little interval. Notice that as it's getting closer and closer and closer and closer to 2, it looks like it's stopping around the y value of 1. So the function or the limit as x approaches 2 from the right would be 1. Versus if we were looking at example E, it's the same x value but now from the left side. Okay, that means we're looking over here. Notice as this is getting closer and closer to 2, it looks like it is going to stop around the -1 y value. Okay. So what I would do is I would pause it, try to answer the rest, and then unpause it, and I will give you the answers to check your work. Okay, so you should have got filling in the left side first. 2 does not exist, does not exist, -1, 2, 2, 2, -2, -2. And then before I continue on, I want to point out, let's see K right here, okay. The reason why it does not exist is because remember when we looked at our example as x approaches 2 from the left and x approaches 2 from the right? Well, it doesn't exist because the values, no matter if we're coming from the left or from the right, need to be the same. So notice that from the left, we got a -1, but from the right, we got a +1, which means the general limit cannot exist because it does not match up. Okay, now let's look at example 4. Example 4 talks about 3 cases where the limit fails to exist, so does not exist. The first case is when the limit is different on either side. This is the most common, okay, where the limit is different on either side. So to prove that, it wants us to answer this question here. Well, why doesn't the limit as x approaches -1 does not exist for the following f of x? And they even give us a graph to help us out. So what we're going to do is we're going to look at the left side, and then we're going to look at the right side. So we're going to say the limit as x approaches -1 from the right of f of x, and then the limit as x approaches -1 from the left of f of x, and then look at each one. Well, from the right would be this one right here, because this is our -1. So if we're looking at our small boundary around it, that is the only function that goes to the right of that -1 value. Well, notice that is also looking like that it's approaching 1 on the y values. Just like if we look at from the left side, which is going to be this function because it's on the left of that -1 value, it looks like that as x is approaching -1, our function here is approaching -1 as well. However, since 1 does not equal -1, this limit does not exist. The next case is an oscillating behavior. And when you think oscillating, just think back and forth. You mainly see these when you see like trig functions, like in our example here, so sine or cosine. And what it wants us to do is explain why the limit does not exist at x equals 0. Well, first off, if we look at our graph, we know, because we're super smart mathematicians here, that 0 is at the origin. However, notice how there's so much concentration in the function right there where it's going up and down, that we would not be able to pinpoint an exact value for where 0 is on the y-axis. Meaning, if we were to look at the limit on either side, we would not be able to tell what finite value it is. So showing that, we're going to find the limit as x approaches 0 from the right side, and then the limit as x approaches 0 from the left side. So starting with the right side, okay, this is this side here. Notice that it looks like we're going up, and then as we're getting closer to 0, we are going to go down, okay? That's all we can tell from this. So we can't just say equals down, right? That doesn't make sense. So we're going to say, well, instead of it equaling something, we're just going to say it is less than 0, because that's all we can pinpoint. For the left side, we notice that, okay, we're going down, and now we're going up, okay, which tells us that this is greater than 0. Well, again, for 1, these don't match. Okay, we can't say 1 is greater than 0 and 1 is less than 0. We also can't say that these are equal to each other, so that's why the limit does not exist. We need some finite answer to be able to prove that the limit is there. And that leads us to case 3, which is the unbounded behavior. And all this is meaning is that if you look at the graph, you'll notice that it is going to infinity or negative infinity in either direction. And it wants us to prove this by proving that the limit does not exist at x equals 2 for the following function. So like always, we look at the limit from both sides. So the limit as x approaches 2 from the right of f of x, and then the limit as x approaches 2 from the left of f of x. And again, we're going to find 2 here. So here is our 2, and we are going to draw a small interval around that. And we're first going to look at the right side. So that would be this. So as we are getting closer and closer to the 2, our graph is going up towards infinity. And then on the left side, as we're getting closer and closer to 2, our graph is also going up towards infinity. So you might be thinking, well, our limits match on both sides. So why does the limit not exist in this case? And the answer to that is, can you count to infinity? And you can't. Because infinity is not a finite number. It's not a real number. So we can't say the limit exists at infinity because infinity is not a real number. It is a number that goes on and on forever that we can never pinpoint or stop. So that means our answer does not exist. What this is good for, however, is to identify the behavior, and infinity is the behavior of the function f of x. Okay, example 5. So it says, now let's look at it in a different way, maybe a little bit more numerical, okay? Let's say we have the following function. Okay, so this is our function here. Oops. Our function here. And we want to see what the limit would be as x approaches 3. Well, we can solve this numerically by plugging in all types of numbers that are close to 3 on both the left side and the right side. So these values here would be everything to the left of 3, and this value here would be everything to the right of 3. So we're going to plug in each of those x values and see what we get. If you want to take a moment and pause and type this into Desmo so you can get an answer, do that now. Make sure you're rounding to at least 4 decimal places. Okay. This is what you should have gotten: 0.1265, 0.1251, 0.1250, and then undefined. This is very important because if you were to plug in 3 into our function, the reason why we can't just do this in the first place is you would get 0 divided by 0, which is undefined because we cannot divide by 0. And then you would get 0.1249, 0.1248, and 0.1234. And then it says, based on this, can you tell me what the values would be approaching from 3 from the left and approaching 3 from the right? Well, if we look at this, what this is telling us is to look at the values closest to 3, and that would be the 2.999 and 3.001. So that means from the left, our value is 0.125, and if we were to round the right to 3 decimal places, we would also get 0.125, which tells us that the general limit is 0.125. And so if our left side matches our right side, we know the limit exists at a finite number, an exact number, and in this case, it's 0.125. Okay. That leads us to the following, and that is the limit existence theorem. And basically what this is saying is that a limit can only exist if the left and the right side are both equal to a real number. Both equal to a real number. And it tells you it verbally below. And then in example 6, it wants you to take a moment and pause and go ahead and write that theorem in your own words. So it says, in order for a general limit to exist, the function has to do what? And there should be something along the lines that it should approach the same y value from the left and approach the same y value from the right, and then that value must be a number. Okay. Last example here is, okay, now knowing what we know about limits, okay, can we sketch a graph to satisfy each of the conditions? So this first one says f of a is undefined. Well, if f of a is undefined, that tells me, okay, maybe there's an open circle somewhere. Okay. The next one says x is equal to a is a point of discontinuity. That's another way to say hole. So now we're getting a little further. There is an open circle that we call a hole somewhere on our graph. And that the limit as x approaches a exists, which means that we should get the same y value on the left and right side. So if I was to sketch something that looks like that, here is my x, here is my f of x. I know at some point A, it's undefined by a hole. However, I know that both sides of my function are going to approach it's going to approach A at some point, some real number B. So this would be one way to do this example. Of course, there's so many ways that you could have drawn out the function, but this is just one way. And then lastly, we're going to look at this one here. And this one is giving us 3 different conditions. The first one's saying the limit does not exist. Well, if it does not exist, then that means they have to have different y values on the right/left side. That means they're not equal anymore because it does not exist. x is equal to a is a jump discontinuity. A jump discontinuity means we have some type of break in our function where they have to jump from one function to another to be able to continue across the graph. And then lastly, it says f of a is defined. So in order for it to be defined, we know that one of our jump discontinuity points has to be a closed circle for it to be defined. So drawing that out, I know I have some value a where there is a jump discontinuity. So I have like an open circle somewhere and then a closed circle somewhere. And then I know that since this is a limit that does not exist, they're going to go in different directions. Meaning if I was to approach from the left side as x approaches a, it would actually be looking like it's going towards some negative b value. But as x is approaching a from the right side, it looks like it's going towards some positive b value. This proves that the limit does not exist, so meets the first condition. We see a jump discontinuity here. And then lastly, f of a is defined, but it's only defined at negative b.